It's Hill and Monique here, and thanks for tuning in to Dreamy Deep Dive.
As always, this is all audio only, so just relax, settle in, maybe find a comfortable spot.
Yeah, really allow yourself this time away from the phone screen, or perhaps you're listening while driving, just letting the conversation flow.
Or maybe you've decided to simply close your eyes for a bit and really focus on this restorative moment.
And we really want to encourage that, actually, that non-visual engagement tonight. It's just so important, isn't it, for mental clarity?
It really is. We all know how exhausting the constant digital world can be. The screens, the notifications.
Exactly. And by just resting your eyes, by avoiding that constant stream of visual input, you're actively doing something good for yourself. You're easing that eye strain.
Which, so often contributes to headaches and just general stress. It builds up.
Right. And when you allow your brain to process information purely through sound, like you are now, it actually fosters a deeper kind of relaxation.
And sharper focus, too, paradoxically. It's a different kind of attention.
This kind of mindful, focused listening, it also supports healthier posture if you're sitting comfortably.
And studies have shown it can genuinely improve sleep quality, help regulate your mood, and significantly lower overall stress levels. It's quite powerful.
So think of this time, these quiet moments away from all the digital noise, think of it as essential self-care, really.
It's space for mindfulness. It allows your body and your mind to just restore themselves and maybe absorb some complex ideas without that feeling of overwhelm.
Which brings us to tonight. Because tonight, we are embarking on a dreamy deep dive into some of the most, audacious, unsettling,
and frankly, unthinkable truths, or perhaps untruths, whispered about our closest celestial neighbor, the moon.
Yeah. Forget the simple idea you might have of a familiar rock-solid sphere just hanging up there in the sky.
What if the moon is not what they tell you? That's the question we're starting with.
We're definitely stepping into some off-limits territory tonight. What if it's actually a massive, chaotic optical illusion, something just projected onto the sky?
Or maybe a perfect natural map of our own Earth, somehow reflected up there.
Or, going even further, perhaps we should entertain the idea that the entire structure is hidden. An alien-made space station.
It sounds wild, I know, but this is the kind of radical speculation we are putting under the microscope tonight. We're going to really examine it.
That's the provocative hook we're pulling on. And our mission for this full time together is to meticulously contrast these, jaw-dropping fringe theories.
Including those persistent claims that the moon landing was faked, which still circulates so widely.
We'll contrast those against the frankly, explosive and overwhelming scientific evidence. What does science actually tell us about the moon's true origin, its composition, its internal structure?
And then finally, we'll explore some really advanced theoretical physics, ideas that suggest the moon, and maybe, just maybe, the entire universe, might genuinely be a hologram.
So we're connecting the most sort of radical claims of fringe theorists to the absolute bleeding edge of cosmic science. It's going to be quite a journey.
It really is. So settle in, let the sound wash over you, and let's begin this dreamy deep dive.
Okay, so where else can we start but with a controversy that just never seems to fade away? The Apollo missions.
Right. Even after, 5 decades now? And just mountains of evidence, physical samples, data, images. The doubt persists.
It does. And for many people, just rejecting the evidence of what was arguably one of humanity's greatest achievements, it seems almost unbelievable in itself. Why? Psychologically, why are people so compelled to doubt something like the moon landing?
It's a fascinating question, and it goes deep into cognitive psychology. It often speaks less about the moon itself and more about how we, as humans, process information, especially information that might challenge our worldview.
So it's not necessarily about the evidence itself?
Not entirely. A key mechanism at play here is something called confirmation bias, and we all do it to some extent.
Explain that a bit more.
Well, it's an inherent psychological processing error. Basically, we tend to selectively seek out, interpret, and favor information that confirms the beliefs we already hold. And at the same time, we tend to disregard or downplay extensive counter-evidence. Even, the incredibly detailed, redundant data provided by organizations like NASA, which has been vetted for decades.
So if I already have a suspicion, maybe, that governments hide things, or that big projects have secret agendas.
Exactly. You're then psychologically predisposed to latch onto any tiny perceived anomaly in a photo, maybe a shadow that looks wrong to you, or something that doesn't immediately make sense.
And I'd ignore the, 382 kilograms of actual moon rocks brought back.
Yeah.
Physical evidence sitting in labs.
Precisely. You'd focus on the anomaly and dismiss the mountain of physical proof. It becomes this self-reinforcing loop. Your belief gets stronger because you keep finding evidence that supports it while ignoring everything that doesn't.
And is there a link to personality or feelings?
Yes, research has shown links there too. Individuals who tend to score higher on measures of, say, paranoia or general anxiety are statistically more likely to endorse these kinds of conspiracy theories.
Why is that? What's the connection?
Well, it seems that possessing what feels like unique knowledge, this secret information that the rest of the sheeple are missing out on, it provides a significant psychological benefit.
It creates a sense of identity, maybe, being in the know.
Absolutely. It fosters a strong us versus them social identity. They feel like they are part of a select few who are truly enlightened, who see the real truth.
Which must feel quite comforting in a way.
Ironically, yes. It can bolster their beliefs and provide a kind of comforting structure, especially if they feel alienated or rejected by mainstream society. It can make them feel special, maybe even in control, because they possess this hidden truth.
Okay, that provides some context for the mindset. Now let's really unpack the most common, the most specific hoax theories themselves. And let's bring in the hard scientific counter-evidence, straight from the Apollo mission data and subsequent analysis.
Sounds good. Where should we start? There are quite a few classics.
The one that I think still sounds the most genuinely terrifying, if it were true, involves the Van Allen radiation belts.
Yes, the Van Allen belt scare, a cornerstone of the hoax theory.
The claim is basically that these belts of lethal radiation surrounding Earth would have just cooked the astronauts, right? Made the journey impossible.
That's the assertion, yeah. That the radiation levels are so high, traversing them would have subjected the Apollo astronauts to deadly, immediate radiation sickness. And therefore, the missions must have been faked because they couldn't possibly have survived the trip. It's often presented as the smoking gun.
So how did NASA actually handle this? It's a real hazard, isn't it? The belts exist.
Oh, absolutely. The Van Allen belts are very real. Discovered by James Van Allen using data from early U.S. satellites. They consist of charged particles trapped by Earth's magnetic field. And yes, the radiation levels within the most intense parts are significant.
So how did the Apollo missions navigate that? Did they just punch right through the middle?
No, definitely not. The trajectory was very carefully chosen. NASA knew about the belts and planned the flight paths accordingly. Instead of going through the most intense donut-shaped inner and outer belts directly, the Apollo spacecraft utilized trajectories that passed through the regions much more quickly and, crucially, through areas where the radiation intensity is lower. Think of it like skirting the edges.
Okay, so they minimized exposure time and intensity. How long were they actually in the belts, the critical regions?
The total time spent transiting the most intense parts of the belts was less than 2 hours combined for the outbound and return journeys.
2 hours. That doesn't sound like enough time to accumulate a truly lethal dose, does it? Especially if they weren't in the very worst parts.
It isn't. The estimated radiation exposure the astronauts received during that short transit through the intense regions was calculated to be about 18 rads.
18 rads. How does that compare to, say, the levels that cause actual radiation sickness?
It's far, far below the threshold. Significant radiation sickness, the kind that causes severe, measurable illness, typically starts to occur somewhere between 200 and 1,000 rads received over a relatively short period, like a few hours. So 18 rads is really quite low in that context.
And was the spacecraft itself shielded?
Yes, absolutely. The Apollo Command Module and Service Module structure provided significant shielding. The hull, the equipment, the tanks, all of that mass helped to absorb a lot of the radiation particles. It was specifically designed with this hazard in mind.
So careful trajectory, short exposure time, and shielding. What about the total dose for the whole mission? from launch to splashdown.
That's even more telling. The average total dose measured for the astronauts over the entire mission duration, typically around 8 days for the lunar landing missions, was only about 0.18 rads.
0.18 rads. That sounds incredibly low. How does that compare to everyday exposures?
It's very low. It's comparable to the radiation dose you might receive from a standard medical chest X-ray, or about the same as living at high altitude for a year, or taking a few long-haul flights.
So the claim that the journey was simply impossible due to radiation.
It's unequivocally debunked by the physical data. Dosimeters were worn by the astronauts, measurements were taken inside and outside the spacecraft. The radiation levels were manageable and well within safe limits for the mission duration. The hazard was real, but it was understood and mitigated.
Okay, that tackles the radiation. What about the visual evidence? The things people point to in the photos themselves, probably the most viral ones on the internet. The flapping flag and the apparently absent stars.
Right, the photographic anomalies. These are very popular because they seem intuitive, but they rely on misconceptions about physics and photography in the lunar environment.
Let's start with the flag. You see the pictures, the U.S. flag planted by Armstrong and Aldrin, and it looks like it's waving, rippling in the breeze. But there's no air, no wind on the moon.
Exactly. That's the core of the argument doubters make. No wind, so the flag can't move or ripple. Therefore, the photos must be fake, taken in a studio with a fan.
But that's not what's happening.
No. It's a great example of an optical illusion based on misinterpreting the setup. The flag was never intended to just hang limply like it would on Earth. NASA knew there was no air to make it unfurl properly.
So how do they make it visible?
It was mounted on a pole with an extendable horizontal bar along the top edge. The idea was to make it look somewhat unfurled and visible for the photographs. However, the astronauts had some trouble fully extending this horizontal bar.
Ah, okay.
And the nylon flag material itself had been tightly folded during transit. So when they deployed it and planted the pole into the hard lunar ground, they inevitably jostled it. The combination of the partially extended bar and the creases from being folded gave the flag that distinctly wrinkled, rippled appearance.
So the shape was fixed, it wasn't actually moving.
Precisely. The metal support structure, the pole and the bar, held it in that bent, rippled shape. It was stuck like that. It was not flapping or moving dynamically in any way. The wrinkles were permanent for the duration it was standing there.
Okay, that makes sense. What about the missing stars then? When you look at the photos from the moon, the sky is just pitch black, ink black. Shouldn't space be full of stars? It seems impossible they wouldn't show up.
The stars are there, of course, billions of them. The issue isn't their absence, it's camera exposure. It comes down to basic photography principles.
Explain that. Why wouldn't they be captured?
Think about the environment. The lunar surface, during the lunar day when the astronauts were there, is incredibly bright. It's bathed in direct, unfiltered sunlight. There's no atmosphere to scatter the light.
Right, very harsh lighting conditions.
Extremely harsh. And the astronauts' spacesuits themselves were bright white and highly reflective to help manage heat. So you have this incredibly bright foreground, the lunar landscape, the equipment, the astronauts.
Okay.
Now, to take a properly exposed photograph of that bright foreground, the photographer, the astronaut, has to use a very fast shutter speed and a small aperture setting. Basically let in only a tiny amount of light for a very short time.
Otherwise, the picture would be completely washed out.
Exactly. If they use the settings needed to capture the foreground correctly, the exposure time is far too short to register the relatively faint, distant pinpricks of starlight. Stars are bright, but compared to the sunlit lunar surface right in front of the camera, they are incredibly dim.
So if they had tried to capture the stars?
If the camera had used a long exposure time and a wide aperture, the settings necessary to gather enough light from the faint stars, then the entire foreground, the astronauts, the lander, the surface, everything important they were documenting would have been completely overexposed as a big, white, useless blob.
It's a limitation of the camera's dynamic range, basically. It can't capture extreme brights and extreme darks in the same shot.
Precisely. You have to choose what you want to expose for. NASA wanted clear pictures of the activities on the surface. The laws of photography explain the absence of stars in those specific images, not a conspiracy involving a studio set.
Makes sense. And beyond the photos and the radiation belts, isn't there even more direct, modern evidence confirming the landings actually happened? Something orbiting the moon right now.
Absolutely. The ultimate, irrefutable proof, if any more were needed, comes from modern orbital reconnaissance. Specifically, NASA's Lunar Reconnaissance Orbiter, or LRO.
What is the LRO?
It's a spacecraft that has been orbiting the moon since 2009, equipped with high-resolution cameras. Its mission includes mapping the lunar surface in incredible detail.
And it's photographed the Apollo landing sites.
Yes, LRO has captured stunningly clear, high-resolution images of all 6 Apollo landing sites.
What can you actually see in those images?
You can see the descent stages of the Apollo lunar modules, exactly where they were left decades ago. They show up clearly as distinct objects on the surface.
Wow. Can you see anything else, like evidence of the astronauts' activities?
Incredibly, yes. The LRO images are so detailed, especially when the lighting conditions are right, that you can even make out the tracks left by the lunar roving vehicles the moon buggies used on the later missions.
You can see the tire tracks.
Yes, faint lines crisscrossing the surface near the landers. And even more amazing, in some images, you can discern the faint, disturbed pathways where the astronauts walked, their footprints.
Footprints still visible after 50 years. How is that possible?
Because the moon has essentially no atmosphere. There's no wind, no rain, no weather to erode or cover those markings. Micrometeorite impacts very slowly degrade the surface over millions of years. But on the timescale of decades, those footprints and tracks remain perfectly preserved exactly where they were made.
So we have photographic evidence from orbit showing the hardware and the paths taken. That seems pretty conclusive.
It really is. Anyone can access these LRO images online on NASA's websites. It's direct visual confirmation from an independent, modern source that the missions happened and the equipment is still there.
Okay, so moving on from the landing hoax theories, which seem thoroughly debunked by physics, photography, and modern observation, we get into the truly bizarre structural theories about the moon itself.
Right. This is where the speculation gets even more, shall we say, creative.
Let's tackle the idea of the hollow moon first, and then the related, even more outlandish spaceship moon concept. What's the fundamental argument people use to suggest the moon might be hollow inside?
The foundational argument, the one you hear most often, relies entirely on a comparison of density.
Yeah.
Proponents correctly point out that the moon's average or mean density is about 3.3 grams per cubic centimeter. That's 3.3 GC meter easy.
And how does that compare to Earth?
They then correctly point out that this is significantly less dense than Earth, which has an average density of about 5.5 grams per cubic centimeter.
So 3.3 versus 5.5. That is a noticeable difference.
It is. And to the proponents of the hollow moon theory, this density deficit is presented as proof positive. They argue there must be a massive empty void inside the moon. It has to be hollow, or at least partially hollow, to account for its overall lighter mass relative to its size.
But this comparison, just looking at the average density, it seems like it fundamentally misunderstands how planets and large moons are structured internally, doesn't it? The concept of differentiation.
Precisely. That's the key scientific point that refutes the simple density argument. We need to remember how large celestial bodies like planets and moons form and evolve. Early in their history, when they were molten or partially molten, heavier elements sank towards the center under gravity, while lighter materials floated towards the surface.
That's differentiation. Earth went through that.
Yes. Earth is dense primarily because during its formation, the heaviest stuff, mostly iron and nickel, sank down to form a large, very dense metallic core. That core makes up a significant fraction of Earth's total mass and volume, pulling the average density way up to 5.5 GCM.
And the moon? Did it differentiate too?
Yes, the moon is also understood to be a differentiated body. We know it has a distinct crust, mantle, and a small core. However, the scientific reality, confirmed by multiple lines of evidence like seismic data and gravity measurements, is that the moon lacks a proportionally large metallic core compared to Earth. Its core is much, much smaller relative to its overall size.
Oh, so less of that super dense material in the center.
Exactly. The moon is mostly made of silicate rock, similar to Earth's mantle, which is naturally less dense than iron and nickel. So the density difference between Earth and the moon isn't evidence of a void. It's exactly what planetary science models predict based on the moon's known chemical composition and its inferred formation history. Specifically, its relative lack of a large iron core. It's expected, not anomalous.
Okay, that tackles the density argument. But there's another piece of evidence often cited for the hollow moon, the really sensational claim about the moon ringing like a bell.
Ah, yes, the lunar bell. This comes from the Apollo seismic experiment.
What's the story there? I've heard it said that after the Apollo 12 astronauts jettisoned their ascent stage, letting it crash back onto the lunar surface.
Correct. It was a planned impact, partly to calibrate the seismometers they had just placed on the surface.
That the seismometers detected vibrations that lasted for a really long time. sometimes cited as almost an hour. That certainly sounds like hitting a large, empty, resonant object, like striking a huge gong or bell.
It is a very vivid claim, and it's true that the seismic signals from that impact, and also from natural shallow moonquakes, were surprisingly long-lasting compared to typical earthquakes on Earth. The ringing description caught on.
So it did ring?
It resonated, yes.
Okay.
But again, the context and interpretation are key. While the vibrations persisted, attributing this solely to a hollow structure is a leap unsupported by the actual seismic data analysis.
So what is the scientific explanation for the long reverberation times?
It's attributed to the unique physical properties of the moon's upper layers, the regolith and the highly fractured crust. Unlike Earth, the moon is geologically dead in terms of active plate tectonics and has no water to dampen seismic waves.
Okay.
Its outer layers are composed of dry, broken rock and dust built up over billions of years of meteorite impacts. This material is very inefficient at damping seismic vibrations. So when a wave starts, it just keeps bouncing around and scattering within this fractured, low-loss medium for a long time before dying out.
Like echoes in a canyon, but with seismic waves and rock.
That's a reasonable analogy. Think of hitting dry sand versus hitting wet clay. The vibrations travel and persist very differently. The dry, unconsolidated, fractured lunar material allows waves to reverberate much longer than the denser, wetter, more consolidated rock layers on Earth, which absorb energy more quickly.
And crucially, did the seismic data show patterns consistent with a large internal void, like waves reflecting off an inner surface?
No. Detailed analysis of the seismic wave propagation patterns, how the waves traveled through the moon from the impacts and moonquakes to the different seismometer stations, did not show the kinds of reflections or behaviors expected if there were a large empty space inside. The data is consistent with propagation through a solid, albeit highly fractured and layered body. The ringing is a surface and near-surface phenomenon related to material properties, not evidence of a giant internal cavity.
Okay, so the density difference is explained by the small core, and the ringing is explained by the dry, fractured rock.
Correct on both counts, according to decades of scientific analysis of the Apollo data and subsequent missions.
Now, these ideas, the low density, the ringing, they all fed directly into an even more extreme theory. The artificial moon, sometimes called the spaceship moon theory. This was famously put forward by two Soviet writers.
Yes, Michael Vosin and Alexander Sherbakov. They published an article in the Soviet journal Sputnik in 1970 titled, "Is the Moon the Creation of Alien Intelligence?"
What was their core argument?
They essentially took the perceived anomalies, the lower density, the surface composition differing from the interior, the ringing, the circular craters, which they argued looked artificial, and proposed that the moon wasn't a natural satellite at all. Instead, they conjectured it was a massive ancient artifact.
An artifact, like built?
Yes. They proposed it was essentially a hollowed-out planetoid, perhaps created by an advanced extraterrestrial civilization countless ages ago. They suggested it might have been encased in a thick, tough shell for protection, and perhaps used as a giant spaceship or observation post.
Wow, that's quite a leap from the data.
It is. Their article was highly speculative, presented more as a thought experiment perhaps, but it tapped into the growing interest in UFOs and ancient astronaut theories that were popular at the time, especially during the Cold War space race era.
And this idea became quite influential in those fringe circles.
Very much so. It became a foundational piece of literature for those who believe in extraterrestrial intervention in Earth's history. They argued that the sheer engineering required to create an object with the moon's specific properties, its size, its orbit, its alleged hollowness, demands an explanation beyond natural processes. It points, they say, to deliberate intelligent design.
And one of our most visually powerful arguments, one that still resonates today, is the perfect eclipse problem.
Ah, yes, the apparent coincidence of the solar eclipse.
It is pretty spectacular, you have to admit. The fact that the moon, from our viewpoint on Earth, appears almost exactly the same size in the sky as the sun. The sun is vastly larger, of course, about 400 times the diameter of the moon. But it's also about 400 times farther away, so their angular diameters, how big they appear in the sky, are almost identical, around half a degree.
Right, and this precise alignment allows for those stunning total solar eclipses where the moon perfectly blocks the sun's disk, revealing the corona.
And proponents of the artificial moon theory point to this and say, come on, what are the chances of that happening naturally? This must be evidence of intentional design. Someone placed the moon at exactly the right distance and gave it exactly the right size to create this perfect visual spectacle for Earth.
It's definitely a compelling coincidence visually. And it's true, total solar eclipses are magnificent phenomena unique to Earth and our solar system in quite this perfect way.
But is it proof of artificiality? What's the scientific perspective on this perfect match?
Well, astronomers are quick to point out a few things. First, the match isn't absolutely perfect, and it's not constant. The moon's orbit is elliptical, not perfectly circular, so its apparent size changes slightly. Sometimes it appears slightly smaller than the sun, leading to annular eclipses where a ring of the sun is visible, and sometimes slightly larger, giving total eclipses.
Okay, so it varies.
Yes, and more importantly, the moon is slowly moving away from Earth due to tidal interactions by about 3.8 centimeters per year.
Which means?
Which means that billions of years ago, the moon appeared much larger in the sky, and total eclipses were more common and perhaps less perfectly matched. And in the distant future, hundreds of millions of years from now, the moon will appear too small to ever fully cover the sun. Total solar eclipses are actually a temporary phenomenon in Earth's long geological history. We just happen to live during the era when the alignment is very close.
So it's a transient coincidence, not a permanent fixture.
Exactly. And secondly, while the perfection of the match is unique to Earth right now, the general phenomenon of moons having apparent sizes similar to the sun from their host planet isn't necessarily unique. Other moons in the solar system can create eclipses. For example, some of Saturn's inner moons, like Prometheus, can have angular diameters very close to the sun's when viewed from Saturn, leading to similar eclipse events.
Wow. Okay, so it's not a totally exclusive property of our system, just the degree of perfection is unusual right now.
Correct. So the scientific community views this apparent coincidence through the lens of orbital mechanics, probabilities, and the long-term evolution of the Earth-Moon system. It's seen as a fascinating but ultimately natural consequence of how the system formed and changed over time, not as evidence of artificial construction by ancient aliens.
Okay, we've tackled the fake landings, the hollow moon, the spaceship moon. Those seem pretty well countered by mainstream science. But now we need to cross into territory that feels even more, well, radical, truly out there.
Indeed. We're now moving beyond physical structure alterations to questioning the moon's very physical existence in the way we understand it.
Let's explore this suggestion that the moon isn't a solid physical object orbiting out there in space at all, but rather, and this is a direct quote from one line of thinking, a natural holographic phenomena having an electromagnetic and optical nature.
Yes, this theory takes the fringe idea of the moon being some kind of map to its most literal and perhaps most bizarre extreme.
How so? What does it actually claim the moon is?
This theory claims that the moon is, quite literally, a projection of Earth itself onto the sky. It's not just analogous to a map, it is the map made manifest optically.
A projection of Earth, how does that work?
The proponents argue that if you carefully study selenography, which is the geography of the moon, the structure of its surface features, you'll find that the major craters, Maria, the dark seas, and other features strongly correspond to the shapes and positions of known Earth continents.
Seriously? They claim to see continents in the moon's features.
Yes, specifically they often point to shapes that they interpret as mirroring the outlines of the American continents, Australia, and Africa. They suggest the moon serves as a kind of real-time natural map of Earth's surface projected above us.
That's a very different view of lunar geology. So this theory implies that the accepted idea of the moon being made of rock, basalt, regolith, that's all wrong.
Completely wrong, according to this theory. They argue that the conventional model of a rocky composition is actually obsolete.
So if it's not rock, what do they propose the moon is made of? If it's a projection?
They argue that the moon's substance is closer to plasma matter.
Plasma, like in a neon sign or the sun?
Essentially, yes. An ionized gaseous substance, a state of matter with distinct electromagnetic properties. They sometimes cite the moon's ability to emit a very faint intrinsic light, even when not directly illuminated by the sun, like during Earthshine, as evidence for this plasma nature.
And how does plasma explain things like tides? We know the moon's gravity affects tides.
In this model, they suggest it's the electromagnetic properties of this lunar plasma that interact with Earth's oceans and atmosphere to cause tides, rather than gravity from a solid body. A conventional solid rock couldn't exert this kind of influence in their view. It requires this active, energetic plasma state.
Okay, this raises a massive question. If the moon is this plasma projection of Earth, how is this hologram, this projection, actually generated? What's the mechanism proposed by this radical theory?
The mechanism is described as the theory of reflected solar rays. It's quite elaborate.
Go on.
The central idea is that the solar energy, the sunlight, that hits Earth's surface, both the oceans and the land masses, isn't just absorbed or reflected diffusely back into space and lost.
Okay.
Instead, according to this theory, these reflected solar rays somehow condense or coalesce, perhaps interact with Earth's magnetic field, and ultimately form the visible lunar phenomenon at a specific altitude.
Where? Not out at 384,000 kilometers.
No, much closer. Perhaps within the magnetosphere or the ionosphere, which they envision acting as a kind of celestial dome or projection screen surrounding the Earth. The moon, in this view, is essentially Earth's own massive physical reflection, somehow solidified or made visible in the upper atmosphere or near space environment.
Wait a minute, hold on. If the moon is a direct reflection or projection of Earth's surface features, that has absolutely staggering implications for the geometry, for the shape of the Earth itself.
It absolutely does. This projection theory cannot work with our standard understanding of Earth as a globe. It carries a monumental, non-negotiable prerequisite.
Which is?
It can only work geometrically if the surface of the Earth is essentially horizontal or flat, perhaps slightly convex, with the celestial domain, the sky, the stars, the projection layer forming a sphere or dome around a stationary Earth.
So this theory is intrinsically linked to flat Earth or stationary Earth models.
Explicitly, it is fundamentally incompatible with the standard heliocentric globular Earth model. In fact, proponents sometimes use the alleged selenographic map on the moon as proof that the Earth must be horizontal and stationary, because only then could its surface features be projected upwards in such a way. The moon becomes evidence against a globe Earth in their framework.
That's a fascinating, if scientifically unsupported, connection. Using one celestial body's appearance to argue against the fundamental established structure of our own planet.
It's a completely alternative cosmology built around this idea of optical projection.
Let's go back to the mechanism of this projection. If it's reflecting Earth's surface, how do the features we actually see on the moon, the familiar light and dark patches, the man in the moon, how do those correspond to Earth's geography, according to this theory?
That's explained through the concept of albedo.
Albedo meaning reflectivity.
Exactly. Albedo is the measure of how much light a surface reflects. The theory suggests that the differences in albedo across Earth's surface are what create the moon's appearance, the contrast between its bright and dark areas.
How specifically? Which parts of Earth correspond to which parts of the moon?
According to this model, high albedo surfaces on Earth. These are primarily the oceans and large ice flows like Antarctica or Arctic sea ice. These surfaces reflect a lot of sunlight, maybe 70% and 90%. These highly reflective areas on Earth condense, supposedly, to form the clear, bright parts of the moon, the lunar highlands, low albedo surfaces on Earth. These are the bare land surfaces, continents, deserts, perhaps dense forests. These surfaces absorb more sunlight and reflect less, maybe up to 30%. These less reflective areas form the dark patches on the moon, the Maria, or seas.
So under this theory, the dark seas on the moon are actually projections of Earth's continents, and the bright highlands are projections of Earth's oceans and ice.
Precisely. It flips the common visual interpretation. The continents become the dark spots, the oceans become the bright background.
And this leads to a concept they call lunar terrestrial cartography.
Yes. The implication is quite extraordinary. They suggest that since the moon, in their model, only reflects or reveals the parts of the Earth's surface that the sun's orbital path is currently crossing or illuminating.
Assuming a sun orbiting a flat Earth.
Assuming that, yes. Then cartographers, perhaps in ancient times or even today, could theoretically use the moon as a kind of live, dynamic, geographical reference point.
To map Earth.
To map Earth. They even suggest it could be used to map potentially unknown or hidden lands, perhaps in the vast Pacific or Indian Oceans, areas that might not be directly illuminated by the orbiting sun in the same way at that moment, but whose reflection still contributes to the lunar image. The moon becomes the fundamental geographical map and reference.
It's a remarkably detailed and all-encompassing alternative view. It ties together ideas about plasma physics, ancient concepts of celestial bodies having direct utility for navigation or mapping, and fundamentally a non-globular stationary Earth model.
It certainly presents a coherent, though scientifically refuted, alternative picture of the cosmos.
Okay. We've definitely wandered far into the realms of radical speculation there. It's important to understand these ideas exist. But now, let's firmly anchor ourselves back to the material reality, the physical measurements, the constraints imposed by decades of scientific investigation.
Absolutely. It's crucial now to pivot back to the hard, physical evidence. The numbers, the data collected over decades, from the seismometers left by the Apollo missions, from the analysis of those hundreds of kilograms of returned rock samples, and from precise orbital gravity measurements made by various spacecraft.
Right, because these constraints imposed by geophysics, the physics of the moon's interior, and geochemistry, its chemical makeup, they offer a highly detailed and frankly non-negotiable picture of what the moon is actually like inside and where it came from.
They paint a picture that is fundamentally incompatible with the hollow, artificial, or holographic moon theories.
Okay, so we started by debunking the hollow moon theory using the density argument, saying the lower density is due to a small core, not a void. Is there other geophysical data that confirms the moon is solid inside? You mentioned moment of inertia earlier.
Yes, the moon's moment of inertia, or MO, is a really powerful constraint.
Remind us what that measures again.
Moment of inertia basically measures how resistant an object is to changes in its rotation. But more importantly for us, it tells us how mass is distributed inside that spinning body. Is the mass concentrated near the center, spread out uniformly, or concentrated near the surface?
Can you give an analogy?
Think of a figure skater spinning. When they pull their arms in close to their body, they concentrate their mass near the axis of rotation, their MOI decreases, and they spin faster. When they extend their arms, they distribute the mass further out, increasing their MOI, and they slow down.
Okay, so MOI relates to mass distribution. What would we expect the moon's MOI to be if it were, say, perfectly uniform density all the way through like a solid homogeneous ball?
For a perfectly uniform solid sphere, the normalized moment of inertia factor should be exactly 0.4.
And what is the moon's actual measured MOI? Based on how it rotates and wobbles?
The moon's actual measured normalized MO is 0.393.
0.393. That's incredibly close to 0.4.
It's extremely close. Now, if the moon were truly hollow, or had a massive void inside, or even if it just had its denser materials concentrated only in a thin shell near the surface, like the spaceship theory might imply, its MOI value would be significantly higher than 0.4, maybe closer to 0.5 or 0.6, indicating mass clustered away from the center.
But it's not higher, it's slightly lower than 0.4.
Exactly. The value of 0.393 confirms a near uniform distribution of mass, but crucially, the fact that it's slightly less than 0.4 tells us that there is some concentration of denser material towards the center. It absolutely requires a solid interior, and it confirms the presence of differentiation, a denser core, surrounded by a less dense mantle and crust. It rules out a hollow structure.
So gravity and rotation confirm a solid, differentiated interior. What about the seismic data? You mentioned the Apollo seismometers recorded the ringing, but what else did they tell us of the layers beneath the surface? They operated for years, right?
Yes, the Apollo Lunar Surface Experiments Package, ALSEP, included passive seismometers placed at the Apollo 12, 14, 15, and 16 landing sites. They operated from 1969 until they were turned off in 1977, gathering a wealth of data.
How many seismic events did they record?
Over that period, they recorded more than 12,000 seismic events. These included vibrations from meteorite impacts, artificial impacts like those planned crashes of ascent stages and SIVB rocket boosters, and thousands of natural moonquakes.
Moonquakes? The moon has quakes.
Yes, though they're different from Earth's. There are deep moonquakes occurring hundreds of kilometers down, likely caused by tidal stresses from Earth's gravity. And there are shallow moonquakes occurring closer to the surface, which are less common but can be stronger and are the ones that ring for a long time. Their origin is less understood, possibly related to cooling and contraction.
And what did analyzing the waves from all these events reveal about the moon's internal structure?
By analyzing how the seismic waves, both P waves and S waves, traveled through the moon, their speeds, their reflections and refractions at different depths, scientists were able to build up a detailed model of the interior. The data constrained the layers quite precisely.
What are the layers?
We have a crust that varies in thickness, but averages around 38 to 45 kilometers thick on the near side, possibly thicker on the far side. Beneath that is a thick mantle, extending down maybe 1,400 kilometers. And beneath the mantle, the seismic data confirmed the presence of a core.
Ah, the core again. What did the seismology tell us about its size? Does it match the MOI data?
Yes, it matches beautifully. Joint inversions combining the seismic data with gravity data, laser ranging data measuring the moon's precise orbit and wobble, and the more constraint all converge on the conclusion that the moon has a small core. The best estimates place the core radius at only about 300 kilometers, plus or minus maybe 20 kilometers.
300 kilometers radius. How does that compare to the moon's total radius?
The moon's total radius is about 1737 kilometers, so the core radius is less than 20% of the total radius.
That is really small proportionally. How small is it in terms of mass?
It's tiny in terms of mass. Calculations suggest the core makes up only about 0.8% to perhaps 1.5% of the moon's total mass.
Compare that to Earth again.
Earth's core radius is about 300 and 485 kilometers, which is over half of Earth's total radius, 6,371 kilometers. And Earth's core makes up nearly a third, about 32% of our planet's total mass.
So the moon having such a small core is the fundamental reason for its lower overall density compared to Earth. It perfectly explains the 3.3 versus 5.5 GC meter difference without needing any hollow spaces.
Exactly. The geophysical data paints a clear picture, solid, differentiated, with a small core, completely refuting the hollow argument.
Now, what about the composition of that small core? Does the geophysics tell us if it's like Earth's core, mostly iron and nickel?
That's a bit more nuanced and still an area of active research. The seismic data suggests the core might have both a solid inner part and a liquid outer part, similar to Earth's. Its exact composition depends partly on what you assume about the composition of the overlying mantle.
How so?
Well, if we assume the lunar mantle has a chemical composition broadly similar to Earth's mantle, which seems likely, as we'll discuss with geochemistry, then the density required for the core to match the seismic and gravity data is around 7,800 kilograms per cubic meter. That density is quite consistent with an iron-nickel, Fnia alloy, perhaps with some lighter elements mixed in.
But what if the mantle composition is different?
Some models suggest the lunar mantle might be richer in iron oxide FeO than Earth's. If that's the case, the overlying mantle is denser, and the required density for the core drops a bit lower, perhaps closer to the 6,100 kilobarimeters. A core that light would imply it couldn't be pure iron-nickel. It would need a significant amount of lighter elements mixed in, like sulfur S or maybe even carbon C.
So there's still some debate about the exact core chemistry.
Yes, refining the core's composition is ongoing work. But the key takeaway is that the evidence points overwhelmingly to a small, dense core existing, whether it's mostly Fe or Fe mixed with sulfur. The interior is complex, layered, and undeniably solid overall.
Okay, that's a very solid picture, literally from the geophysics. Let's move to geochemistry now. This is where the story gets perhaps even more compelling because it provides this incredibly intimate link between the moon and the Earth. What did analyzing those 382 kilograms of rock and soil samples returned by the Apollo missions actually reveal about the moon's chemistry?
The analysis of the Apollo samples and also the robotic Soviet Luna mission samples revolutionized our understanding. Perhaps the most profound finding was the evidence for a deep, shared chemical history between the moon and Earth.
How so? What kind of similarities did they find?
Well, for starters, the composition of the lunar mare basalts, the dark volcanic plains that make up the seas, showed a striking chemical similarity to terrestrial basalts, the kind of volcanic rock found here on Earth, like in Hawaii or Iceland. Similar major elements, similar minerals.
But similarities could just mean they formed under similar conditions, right? Does it prove a direct link?
That's where specific elemental and isotopic tracers come in. These act like fingerprints, revealing a much deeper connection. The similarities extend to highly specific elemental ratios that are quite unusual.
Can you give us a key example, something that really ties them together?
One of the classic examples is the ratio of the element tungsten, Wa, to the element lanthanum, Lo, so the WLA ratio.
Why are those two elements important?
Because they behave very differently during planetary formation. Tungsten, W, is what we call a siderophile element, or iron-loving. When a planet melts and differentiates, tungsten prefers to bond with iron and sinks down into the metallic core. Lanthanum, Lo, on the other hand, is lithophile, or rock-loving. It prefers to stay in the silicate mantle and crust.
Okay, so tungsten goes to the core, lanthanum stays in the mantle. What about their ratio in moon rocks compared to Earth rocks?
Here's the crucial finding. The WLA ratio is highly depleted, meaning much lower in both lunar basalts and terrestrial basalts compared to what we see in primitive meteorites, chondrites, which represent the average building blocks of the solar system.
How much lower?
Lower by a factor of about 20. It's a significant depletion.
And what does this shared unusual depletion tell us?
It strongly suggests that the material that formed the moon was derived from silicate material Earth's mantle that had already experienced the process of core formation. The core had already formed and sunk down, taking most of the tungsten with it, leaving the remaining mantle material depleted in W relative to La. The moon inherited this specific chemical signature from Earth's mantle.
Wow. That's a very powerful chemical clue linking the moon's material directly to Earth's mantle after Earth's core had formed.
Exactly. It argues strongly against scenarios where the moon formed independently or was captured, as those bodies wouldn't likely have undergone this specific depletion process linked to Earth's core formation.
That's already compelling. But you said the ultimate evidence, the one that really creates the paradox we'll discuss later, lies in the isotopic analysis.
Yes. This is generally considered the unambiguous constraint, the smoking gun, if you will, demanding a common origin. We're talking here about high-precision measurements of isotopes.
Remind us what isotopes are again.
Isotopes are atoms of the same chemical element that have the same number of protons but different numbers of neutrons in their nucleus, so they have slightly different masses. For example, oxygen has 3 main stable isotopes: oxygen-16, most common, oxygen-17, and oxygen-18.
And different planets or regions of the solar system tend to have slightly different mixtures of these isotopes for various elements.
Yes, exactly. Variations in isotopic compositions, especially for elements like oxygen, titanium, chromium, and others, act as distinct fingerprints for different planetary bodies and meteorite groups. Mars has a different oxygen isotope signature than Earth. Vesta asteroid fragments have another signature, chondritic meteorites have others. These variations reflect conditions in the early solar nebula where these bodies formed.
So what happens when we measure these isotopic fingerprints for the moon and compare them to Earth's mantle? Specifically, the mass-independent isotopic compositions, which are particularly sensitive tracers of origin.
We look at elements like oxygen O, chromium Cr, titanium Ti, calcium Tk, silicon C, potassium K, tungsten W again, zirconium Zr. The list goes on, and the results are stunning.
What are the results?
They are nearly identical, indistinguishable, within the incredibly fine margins of modern analytical precision.
Identical. Not just similar, but identical.
Essentially, yes. For example, the mass-independent oxygen isotope compositions, specifically EO values of lunar samples and terrestrial mantle rocks, are identical to within about 5 parts per million, ppm. For titanium isotopes, they are identical within about 4 ppm. For chromium, identical within measurement error. Tungsten shows a match reflecting that shared core formation history again. It's uncanny.
5 parts per million identity across multiple different element systems. That sounds statistically impossible. If the moon formed from a different body hitting Earth,
it's extraordinarily unlikely. It's perhaps the single most challenging constraint for models of lunar formation because, as we just discussed, we see significant isotopic variations among all other measured planetary materials in the solar system. Mars is different from Earth. Asteroids are different from Earth. Why would the moon, if it incorporated a significant chunk of an impacting body, Theia, end up looking exactly like Earth's mantle isotopically? Theia would almost certainly have had its own distinct isotopic fingerprint, different from Earth's.
So the isotopic evidence is overwhelming. The moon and Earth's mantle must have shared the same precursor material. They are, isotopically speaking, twins.
Precisely. The similarity is so strict, so pervasive across multiple elements, it essentially acts as an undeniable chemical fingerprint proving a common heritage.
Okay, now, reinforcing this idea of a shared hot origin is the evidence of volatile depletion you mentioned.
Yes, another key geochemical constraint. The moon is strongly depleted in elements that vaporize relatively easily, elements that are more volatile than, say, lithium.
Which elements specifically?
We're talking about elements like potassium K, sodium Na, rubidium Rb, zinc, Zn, lead, Pb, and others. Compared to Earth mantle composition, the moon has significantly lower concentrations of these moderately volatile elements.
How much lower?
For elements like potassium and sodium, the depletion factor is about 5 to 6 times lower than in Earth's bulk silicate composition. For even more volatile elements like zinc or lead, the depletion is even more severe.
And what does this depletion tell us about the conditions under which the moon formed? It suggests high temperatures were involved, right, to boil off these elements.
Yes, it definitely points towards a high-energy, high-temperature event being involved in the moon's origin, capable of vaporizing these elements. However, there's the crucial subtlety here regarding the temperature at which this loss occurred.
Was it subtle?
Detailed thermodynamic modeling, combined with looking at isotopic fractionation patterns within some of these volatile elements, like potassium and zinc isotopes, which show slight enrichment in the heavier isotopes on the moon, suggests that this volatile loss couldn't have happened at extremely high boiling temperatures from a large molten body.
Why not?
Because extremely high temperatures tend to cause kinetic fractionation that doesn't match the specific isotopic patterns observed. Instead, the evidence points towards the depletion happening at relatively lower temperatures, perhaps around 1400 Kelvin, which is about 1100 degrees Celsius or 2000 Fahrenheit.
1400 K? That's still very hot, but maybe not boiling rock hot.
Right. It's hot enough to vaporize these elements significantly, but perhaps cool enough to allow for the specific kind of equilibrium isotopic fractionation that is observed. This relatively low temperature requirement is vital.
Why is it so important? What does it rule out?
It poses a challenge for some formation models. It suggests the volatile loss might not have occurred primarily from a huge, fully formed magma ocean on the moon, or from a super hot, vapor-dominated disk right after impact. Instead, it might imply that the loss happened more effectively from smaller precursor materials, perhaps millimeter or centimeter-sized droplets or particles, condensing in the debris disk before they fully accreted to form the moon. The volatiles escaped more easily from these smaller bits at around 1400 K.
Okay, so that adds another layer of complexity. High energy event, yes, but volatile loss, potentially constrained to a specific, not quite maximum temperature window. Right, so let's recap the constraints we've gathered from the science. We need a model that explains a moon that's solid, differentiated with a small core from geophysics. A moon that is chemically and isotopically identical to Earth's mantle from geochemistry, the WLA ratio, the isotopes. A moon that's significantly depleted in volatile elements, with that loss occurring around 1400 K, geochemistry. And of course, a model that accounts for the Earth-Moon system's total angular momentum and the moon's orbit. That's a daunting list of demands.
It truly is. Each constraint is quite strict, and satisfying all of them simultaneously has proven incredibly difficult for planetary scientists. Now we have to ask, which dynamical model, which scenario for how the moon actually formed can possibly satisfy all of these demands?
Let's start by quickly reviewing the historical models that were proposed before or alongside the current leading theory. Why are they no longer considered viable? You mentioned fission, capture, and co-accretion earlier.
Right. We should briefly dismiss those first because they simply fail to meet these key constraints.
Okay, first, the fission hypothesis. This was the idea, proposed by George Darwin, Charles Darwin's son, back in the 19th century, that the early Earth was spinning extremely rapidly, so fast that a blob of molten material was flung off from its equator, which then coalesced to form the moon. Some even suggested the Pacific Ocean basin was the scar left behind.
It's a dramatic idea, but it fails spectacularly on several counts. Firstly, the physics of angular momentum just don't work. For Earth to spin fast enough to fission off the moon, it would require an initial rotation period of maybe 2.5 hours. The current Earth-Moon system has a lot of angular momentum, but not that much. There's no known mechanism to dissipate the excess angular momentum required by fission.
And chemically?
Chemically, if the moon came purely from Earth's mantle, it might explain the isotopic similarity, but it doesn't easily explain the moon's specific depletion in volatile elements compared to Earth's mantle, nor why its overall composition isn't exactly the same. He, iron content. And the Pacific Basin idea is geologically incorrect. The ocean floor is much younger than the moon, so fission is out.
Okay. Next, the capture hypothesis. The idea that the moon was a fully formed, independent planetary body wandering through the solar system that just happened to pass too close to Earth and got gravitationally snagged into orbit.
This was popular for a while too. The main problem here is dynamics. Gravitational capture is actually incredibly difficult. It requires very specific conditions, usually involving a third body or a temporary atmosphere to dissipate energy. It's dynamically improbable for a body as large as the moon to be captured into a stable, near-circular orbit like it has.
And the chemistry and isotopes.
They completely rule out capture. A captured object would almost certainly have formed elsewhere in the solar system, perhaps in the asteroid belt or even further out. It would therefore likely have a very different bulk composition, maybe more chondritic, richer in volatiles and iron, and crucially, it would have a vastly different isotopic signature, oxygen, titanium, chromium, etc., compared to Earth. The observed isotopic identity makes simple capture essentially impossible.
Right, the fingerprint doesn't match anything else out there. Okay, third, the co-accretion hypothesis, sometimes called the binary accretion model. This suggests Earth and the moon formed together, side by side, accreting material from the same region of the protoplanetary disk, like sister planets.
This model has trouble explaining the angular momentum of the system. It's hard to get the moon orbiting Earth rather than just falling into it or orbiting the sun independently. But the biggest failure is chemical. If they formed side by side from the same reservoir of material, the moon should have roughly the same overall bulk composition as the Earth.
Which would mean?
Which would mean the moon should have a much larger iron core, proportional to Earth's core maybe making up 30% of its mass. But as we know from the geophysical data, MAR, seismology, the moon has a tiny core, maybe 1.5% of its mass. So co-accretion fails to explain the moon's iron pore composition compared to Earth.
So fission, capture, co-accretion all fail based on dynamics, chemistry, or both?
Correct. By the time of the Apollo missions and the sample returns, these models were already facing serious problems, and the new data essentially rendered them non-viable.
Which brings us to the reigning theory, the one developed largely in response to the Apollo findings. The Giant Impact Hypothesis, or GIH.
Yes. Proposed independently by William Hartman and Donald Davis and Alistair Cameron and William Ward in the mid-1970s. This quickly became the canonical or standard model for a lunar formation.
What's the basic scenario in the GIH?
The core idea is that late in the formation of the solar system, about 4.5 billion years ago, the proto-Earth, the nearly formed Earth, was struck by another large planetary body, roughly the size of Mars. This hypothetical impactor is often nicknamed Theia, after the Titan goddess who was the mother of Selene, the moon goddess in Greek mythology.
A Mars-sized object hitting the early Earth. What happened next?
The impact was colossal, incredibly energetic. It would have ejected a massive amount of molten rock and vaporized material from both the proto-Earth's mantle and from Theia into orbit around the Earth. This ejected material formed a hot, dense debris disk. Over a relatively short timescale, maybe centuries or millennia gravity, caused the material in this disk to coalesce and accrete, eventually forming the moon.
What advantages does this model have? Why did it become the leading theory?
The GIH was immediately attractive because it could naturally explain several key features. 1. Angular momentum. A large, off-center impact could easily impart the high angular momentum observed in the Earth-Moon system today. 2. Iron poor moon. If the impact was somewhat grazing, most of the iron core of the impactor, Theia, might have merged with Earth's core, while the debris disk that formed the moon would be composed mostly of the silicate mantles of both Earth and Theia. This naturally explains why the moon is depleted in iron and has a small core compared to Earth. 3. High temperatures. The sheer energy of the impact would generate immense heat, potentially explaining the evidence for melting, like the inferred early lunar magma ocean, and the depletion of volatile elements.
Okay, so it seemed to solve several big problems at once. It explained the orbit, the small core, the heat. It sounds like a great fit.
It was considered a great fit, and it remains the best overall framework we have. However, this is where the paradox really emerges. As our analytical techniques improved, especially for high-precision isotope measurements in the 2000s and 2010s, the giant impact hypothesis ran into a profound fundamental flaw when confronted with those stringent geochemical constraints we just spent time detailing.
And this is the isotopic dilemma.
Exactly. It's the absolute core of the problem with the standard GIH.
What is the dilemma specifically?
The canonical GIH model, simulated using computer models, called smoothed particle hydrodynamics, or SPH simulations, consistently predicts that the moon, formed from the debris disk, should not be made mostly of Earth material. Instead, the simulations show the disk, and thus the moon, should retain a significant portion, typically calculated to be somewhere between 40% and maybe even 80% in some models of material originating from the impactor, from Theia.
So the moon should be mostly made of Theia, not Earth.
Or at least a significant mixture, heavily weighted towards Theia. But here's the killer point. Unless Theia, this Mars-sized body, just happened by sheer unbelievable coincidence to have the exact, statistically near impossible, identical isotopic signature to the proto-Earth across multiple elements: oxygen, titanium, chromium, tungsten, etc.
Which goes against everything we understand about material variation in the early solar system.
Right. Planets forming in different locations should have different isotopic fingerprints. So if the moon is mostly Theia, or even a 50-50 mix, it should not be isotopically identical to Earth's mantle. It should show a clear isotopic difference reflecting the contribution from the isotopically distinct Theia.
But the data says they're identical.
Precisely. The data shows near-perfect isotopic identity. The standard GIH model predicts they must be different. That's the isotopic dilemma. The canonical model fails spectacularly to explain the moon's most precise chemical fingerprint.
So, faced with this massive contradiction, scientists have been trying to modify the giant impact scenario, right? Trying to find ways to force a perfect mix or somehow derive the moon mostly from Earth. despite the impact dynamics.
Exactly. The challenge has been to tweak the impact parameters or the post-impact physics to resolve this dilemma while still satisfying the other constraints. Angular momentum, small core, etc. Several potential solutions have been proposed.
What's one approach? Changing the impact itself.
Yes. One key idea involves changing the nature of the impactors. Instead of a smallish Theia hitting a large proto-Earth, maybe the collision involved two bodies that were much closer in size. This is sometimes called the half-Earth impact model.
A collision between two roughly equal half-Earth-sized planets.
Exactly. Simulations suggest that such a massive energetic collision between two large, already differentiated bodies could generate much higher temperatures and pressures, leading to more vigorous and effective mixing of the mantle materials from both colliding objects and the resulting debris disk.
So better mixing could potentially homogenize the isotopes, erasing the original difference between the two bodies.
That's the hope. If the mixing is efficient enough, the resulting moon could plausibly inherit an isotopic signature very close to the average of the two identical-sized impactors, which, if they formed near each other, might have been more similar to begin with, though still likely distinct. This model more naturally explains the isotopic similarity.
Are there problems with the half-Earth model?
It requires a very specific, perhaps less probable type of collision, and generating the current Earth-Moon angular momentum from such a symmetric impact can be challenging in some simulations. It's a viable path, but not without its own difficulties.
Okay, what's another, perhaps even more exotic, proposed solution? You mentioned the concept of a synestia earlier. That sounds really unusual.
It is. The synestia model, proposed by Simon Locke and Sarah Stewart, suggests that some giant impacts, perhaps especially those involving high energy and high angular momentum, don't just create a simple debris disk. Instead, they can form a completely new temporary astronomical structure called a synestia.
What is a synestia?
Imagine a huge, rapidly rotating donut-shaped structure made mostly of vaporized rock. It's so hot and spinning so fast that the outer edge rotates at orbital velocity. There's no distinct surface separating the protoplanet from its disk. They merge into one continuous swirling mass of supercritical fluid, part gas, part liquid. The Earth essentially becomes a giant vaporous donut for a short time.
Wow. And how does it help with the isotope problem?
The key idea is that within this incredibly hot, turbulent, vapor-dominated synestia structure, the material from the proto-Earth's mantle and the impactor's mantle would mix extremely rapidly and thoroughly due to convection and turbulence. The intense heat and pressure would effectively homogenize the silicate material before the structure cooled down enough for the moon to start condensing from silicate droplets within the vapor.
So, the synestia acts like a giant cosmic blender, specifically designed to erase any pre-existing isotopic differences between Earth and Theia.
That's a good way to put it. The synestia model is appealing because it provides a plausible physical mechanism for achieving the required isotopic equilibration naturally as a consequence of these extremely energetic impacts. The moon then condenses from this already mixed vapor cloud.
Okay, that sounds promising for the isotope identity. But what about our other key constraint? The volatile element depletion, especially that 1400 K temperature window. Does the synestia model or even the half-Earth model handle that well?
Therein lies the rub. This is the volatile loss challenge, and it's a major hurdle for most high-energy impact models, including synestias. Because these models, especially synestia, which involves extensive vaporization, predict extremely high temperatures in the debris disk or synestia structure, potentially thousands of degrees Kelvin, much hotter than 1400 K. At those extreme temperatures, you'd expect very efficient, near-complete vaporization of not just moderately volatile elements like potassium and sodium, but possibly even more refractory ones.
So they predict too much volatile loss, maybe, or loss under the wrong conditions.
Potentially, yes, or loss that doesn't match the specific patterns observed. They struggle to explain why the volatile depletion seems to have occurred under conditions equivalent to that relatively cool 1400 Kelvin window, as suggested by the thermodynamic modeling and isotopic fractionation data for elements like potassium and zinc. High-temperature, kinetically controlled evaporation might produce different isotopic fractionation patterns than what's observed.
So the models that are good at mixing isotopes, like synestia, might be bad at preserving the right volatile signature, and vice versa.
That's often the trade-off, yes. It's very difficult to find an impact scenario that simultaneously achieves perfect isotopic mixing and results in the specific pattern of volatile depletion seemingly set at 1400 K. Some recent refinements try to model condensation and volatile loss within the cooling synestia, but it remains a significant challenge.
This leaves us in a rather unsatisfying place scientifically, doesn't it?
It really does. It leads to what many lunar scientists acknowledge as the current state of affairs. The somewhat stark, unambiguous conclusion that, quote, there is no one dynamical model that satisfies all geochemical and geophysical properties of the moon.
Wow, no single model works perfectly.
Not yet. The extreme chemical and isotopic similarity provides incredibly strong evidence that the moon was derived almost entirely from Earth's mantle material after Earth's core had already formed. That part seems almost undeniable from the geochemistry. The fundamental problem is our current understanding of impact dynamics makes it very difficult to achieve that outcome, deriving the moon mostly from Earth from a giant collision, which seems necessary for the angular momentum and iron depletion. The physics seems to require a massive impactor, but the chemistry provides almost no unambiguous evidence that this massive, isotopically distinct impactor ever contributed significantly to the moon's makeup. It's a genuine paradox.
Okay, we've established the moon is solid, it's chemically tied to Earth almost identically, but its exact formation story remains a profound paradox, a puzzle that physics and chemistry are still struggling to solve completely. Now let's do something interesting. Let's take that initial, very fringe holographic idea we discussed the moon as a plasma projection and connect it, perhaps surprisingly, to some of the deepest, most mind-bending concepts about the structure of reality itself, coming from theoretical physics.
Right. We're going to shift focus dramatically now from the specifics of lunar structure and origin to the ultimate structure of the cosmos. We're moving from the, frankly, scientifically unsupported idea of the moon as a local hologram to the genuinely cutting-edge, though still speculative scientific idea that the entire universe might, in some fundamental way, be a holographic projection.
That sounds even more incredible than a holographic moon. Where does this scientific concept of a holographic universe come from? It sounds like science fiction.
It does sound like science fiction, but it emerges from some of the deepest problems in theoretical physics, particularly the intersection of quantum mechanics and Einstein's theory of general relativity, gravity. The core idea is known as the holographic principle.
The holographic principle, what does it propose?
In essence, it's a principle within quantum gravity that proposes that the full description of a volume of space, like the 3D room you're in, or even the entire observable universe, can actually be thought of as being encoded on a lower dimensional boundary surrounding that space, typically like information stored on a 2D surface at the edge of the volume.
Like a real hologram, where a 2D film encodes a 3D image.
Exactly like that. That's where the name comes from. A hologram stores all the information needed to reconstruct a 3D image on a 2D photographic plate. The holographic principle suggests that the universe itself might work in a similar way, that the 3D reality we perceive might be fundamentally projected from information encoded on a distant 2D boundary surface.
Where did such a radical idea even originate within physics? It seems counterintuitive that volume could be an illusion.
It originated primarily from theoretical studies of black holes starting in the 1970s with work by Jacob Bekenstein and Stephen Hawking.
Black holes. How do they lead to holography?
It started with black hole thermodynamics. Bekenstein was studying the entropy of black holes. Entropy is usually thought of as a measure of disorder, or fundamentally the amount of information required to describe a system. Normally, you'd expect the entropy or information capacity of an object to scale with its volume. A bigger box can hold more stuff, more information.
Makes sense.
But Bekenstein discovered something astonishing. He found that the maximum entropy, the maximum information content that could be contained within any region of space containing a black hole, does not scale with the volume of the region. Instead, it scales with the surface area of the black hole's event horizon, the boundary from which nothing can escape.
The information scales with the area, not the volume.
Yes. This is known as the Bekenstein bound. It suggests that the information content of a black hole, and perhaps any region of space, is limited by its boundary area, measured in tiny units called Planck areas. This was a profound shock. It hinted that maybe volume isn't the fundamental measure of information capacity. Area is.
And how does this help with things like the black hole information paradox? The question of what happens to the information about things that fall into a black hole, which Hawking initially suggested was destroyed.
It provides a potential resolution. If all the information about the objects that fall into the black hole isn't lost inside the unknowable singularity within the volume, but is instead somehow encoded or smeared out across the 2D surface of the event horizon, then the information isn't truly lost when the black hole eventually evaporates via Hawking radiation. It's preserved on the boundary. This implies, again, that the fundamental reality might reside on the boundary, not within the volume. the concept of volume itself might be fundamentally illusory or emergent.
So, the implication is that the physical world we experience, matter, energy, space, time, might just be secondary, incidental perhaps, and that the universe is fundamentally made of information.
That is the radical implication that physicists like Wittgenstein, Gerard Hooft, and Leonard Susskind began to explore. The idea that perhaps information is the most fundamental currency of reality. Wittgenstein himself argued that thermodynamic entropy, measuring disorder in physics, is conceptually equivalent to information entropy, as defined by Claude Shannon in information theory. They are two sides of the same coin.
And the holographic principle takes this insight from black holes and generalizes it.
Yes. Hooft and Susskind proposed that this principle, that the degrees of freedom describing a volume reside on its boundary, might not just apply to black holes, but to the entire universe. The idea is that the physical world we perceive in 3 spatial dimensions might be nothing more than a holographic projection, a manifestation of information inscribed on some distant, vast, 2-dimensional surface at the cosmological horizon, the edge of the observable universe.
That is genuinely mind-bending. Our 3D reality as an illusion projected from a 2D screen at the edge of everything. Has this principle been mathematically realized in any concrete way? Or is it just a philosophical idea?
It's more than just philosophy. While a full theory of quantum gravity that incorporates it is still lacking, there has been a major breakthrough in realizing the holographic principle mathematically within the framework of string theory. This is the AD-CFT correspondence.
AD-CFT, what does that stand for?
It stands for Anti-de Sitter Conformal Field Theory Correspondence. It was proposed by physicist Juan Maldacena in 1997 and is often called the Maldacena duality.
What does it connect?
It's a powerful, mathematically precise conjecture, though not yet rigorously proven in all cases, that demonstrates an exact equivalence or duality between 2 seemingly very different types of physical theories. 1, a theory of quantum gravity, specifically string theory or M theory, living in a negatively curved spacetime called anti-sitter space, ADS, which has, say, 5 dimensions. 2, a standard quantum field theory, specifically a conformal field theory, or CFT, which has no gravity, living on the flat 4-dimensional boundary of that ADS space.
So a theory with gravity in a higher dimension is mathematically equivalent to a theory without gravity in one lower dimension, living on its boundary.
Exactly. It's like a mathematical dictionary that allows you to translate problems from the difficult language of quantum gravity in the bulk, the volume, into the often easier language of quantum field theory on the boundary, the surface, and vice versa. The 2 descriptions, though vastly different, contain precisely the same information and predict the same physical outcomes.
And this AD-CFT correspondence is considered the most successful theoretical realization of the holographic principle.
Yes, by far. It provides a concrete mathematical framework demonstrating how a higher dimensional reality with gravity can emerge holographically from a lower dimensional theory without gravity living on its boundary. While our universe isn't exactly anti-de Sitter space, it seems to be closer to flat or slightly positively curved de Sitter space, especially with dark energy, the AD-CFT correspondence provides strong theoretical evidence that the holographic principle might be a fundamental feature of quantum gravity. It suggests our perceived 3D reality plus time could indeed be mathematically encoded in a lower dimensional theory.
It sounds incredibly abstract and mathematical. Is there any way physicists are trying to find tangible experimental evidence for this holographic nature of reality? Can we test if our 3D world is really a projection?
That's the ultimate challenge, of course. Moving from mathematical conjecture to experimental test, it's extremely difficult because the pixels of space-time, if they exist, are thought to be incredibly tiny on the order of the Planck length, about 10 meters, far smaller than anything we can probe directly.
For how could we possibly detect any effect?
One approach, pioneered by physicists like Craig Hogan at Fermilab, was to look for potential macroscopic consequences of this assumed microscopic graininess or fuzziness of spacetime predicted by some interpretations of the holographic principle. They argued that if spacetime itself is fundamentally built out of discrete bits of information, like pixels on the holographic boundary, then there might be an inherent uncertainty or noise in the measurement of position itself.
Like spacetime itself is jittering slightly at a fundamental level.
Kind of, yes. They called this hypothetical signal holographic noise. The idea was that the limited information content allowed by the holographic principle might manifest as tiny, correlated quantum fluctuations in spatial position that could perhaps be detectable by extremely sensitive instruments designed to measure tiny displacements, like gravitational wave detectors.
Were these experiments conducted? Like at GEO 600, the detector in Germany?
Yes. Hogan suggested that the GEO 600 detector might be sensitive enough to potentially detect this specific kind of holographic noise, which was predicted to have a characteristic frequency spectrum. There was some excitement around 2008-2009 when some unexplained noise was found in GEO 600 that vaguely resembled the prediction, but further analysis and upgrades eventually ruled it out as being the holographic signal. Similar searches using other instruments have also yielded null results so far.
So no direct evidence for holographic noise yet?
Not yet, at least not matching those specific early predictions. It's possible the noise exists but is much smaller, or has a different character, or that this particular interpretation of how holography manifests is incorrect. However, the very fact that experimental physics is now actively designing and using instruments to probe the fundamental quantum structure of space-time itself, asking questions about whether space is smooth or pixelated, whether reality is truly 3D or a projection, shows just how far this idea has moved.
It demonstrates that what might have started sounding like completely fringe speculation the universe is a hologram is now intertwined with genuine mainstream scientific inquiry at the deepest level, even if the answers are still elusive.
Absolutely. It means that the radical fringe speculation about the moon maybe being some kind of hologram, while based on completely flawed astronomical premises and misunderstandings of physics, it ultimately, perhaps accidentally, echoes the deepest, most complex, and genuinely unsettling questions about the nature of reality that are being asked at the absolute forefront of advanced theoretical and experimental physics today. The universe might be stranger than we think, even if the moon itself isn't a plasma projection. #tag Lillerin. Conclusion.
Well, we have certainly taken a journey tonight on this dreamy deep dive. We started by opening the door, didn't we? To some of the most shocking, the most outlandish claims whispered about our moon.
That it's secretly a hollow spaceship, maybe left by aliens, or perhaps just a trick of the light, a plasma projection onto the sky, somehow requiring a flat Earth to even work. Wild ideas.
And we encouraged you right at the start to perhaps close your eyes, to engage only with the audio, to give your eyes and your mind that much-needed rest from the visual world.
We hope you found that helpful, because we then meticulously contrasted those fringe claims against the weight of scientific evidence. The rock-solid reality, you might say.
Yeah, the data from geophysics, the moment of inertia, the seismic waves traveling through its interior, proving the moon is a solid, differentiated body with a small core. Not hollow.
And the geochemistry, the analysis of those precious Apollo rocks revealing its composition, showing that uncanny, intimate kinship with Earth's mantle, sharing that identical chemical fingerprint down to just 5 parts per million for key isotopes.
Which is just astounding. And that evidence, that isotopic identity, leads us straight into the heart of the modern scientific puzzle, the giant impact paradox.
Right. The canonical theory, the giant impact, seems necessary to explain the moon's orbit and its small core. But that same theory predicts the moon should be made mostly of the impactor Theia, and thus should look isotopically different from Earth. Yet the chemistry provides almost no unambiguous evidence that this impactor ever existed, in terms of its contribution to the moon's makeup.
Forcing physicists to invent these extraordinary, maybe even contrived, solutions like the half-Earth collision or the synestia model, just to try to force that perfect, impossible mixture required by the isotopic data. While simultaneously trying to explain the volatile depletion, it's a huge ongoing challenge.
It really highlights how much we still have to learn about our closest neighbor's birth.
And then, finally, we took that leap. We explored how the seemingly bizarre fringe idea of a holographic moon touches upon, or resonates with, the genuine cutting-edge concepts in theoretical physics. The idea that reality itself, the entire universe, might be an informational projection.
Encoded on some lower dimensional boundary, as suggested by the holographic principle and mathematically realized in things like the ASCFT correspondence. A concept being actively, if inconclusively, probed by experiment.
We really hope you've enjoyed this focused, non-visual engagement tonight. And just a reminder of the benefits. Taking this time away from screens, just listening, it genuinely fosters mental clarity, it eases that physical eye strain, and it offers a crucial restorative moment for both your body and your mind.
Absolutely. It supports healthier posture, can reduce headaches, and really does offer essential space for deeper relaxation, sharper focus, and maybe just letting these big ideas sink in.
So we want to leave you with a final provocative thought to consider as we wrap up this dreamy deep dive. Something to mull over.
Considering that the chemical and isotopic evidence provides essentially no unambiguous evidence for an impactor's contribution to the moon, this implies one of two truly mind-bending possibilities must be true.
Possibility 1.
Either the proto-Earth and the impactor, Theia, mixed absolutely perfectly, instantaneously in an incredibly extreme, high-energy event like a synestia, completely erasing any trace of Theia's original foreign isotopic identity, while somehow also setting the volatile clock to 1400 K. A perfect, almost suspiciously convenient outcome.
Or possibility two.
Or the moon is fundamentally, as some have described it, just a devolatilized fragment of Earth's mantle, whose true origin, the mechanism that put it into orbit, is still fundamentally misunderstood. Perhaps the giant impact hypothesis, while being the best model we have, is ultimately just the worst model we have, except for all the others. Maybe something entirely different happened that we haven't conceived of yet.
So the final question for you to ponder is, which reality is more unsettling? The idea of a perfect, seemingly impossible collision that just happened to create exactly what we see, or the idea that, despite decades of study, everything we think we know about the moon's birth might still be profoundly wrong.
Food for thought indeed.
This has been a truly dreamy deep dive. It's Hill and Monique here, and if you liked what you were tuning into, we really invite you to subscribe to Dreamy Deep Dive. That way you'll get more of this kind of ASMR-like content exploring fascinating topics in the future.
Yeah, and please hit that bell button too, so you'll be notified when we release new explorations. Most importantly, if you found this valuable or interesting, please like this deep dive.
It really helps recommend it to other listeners who might share the same interests. Or, share it with people you think would appreciate this kind of non-visual, brain-enticing, maybe sometimes mind-bending, knowledgeable content.
Thank you so much for listening, for spending this time with us, and we'll catch you next time.